Schrödinger's equation. Few days back, a video was posted about the same thing. That was not Schrödinger's equation. That was about wave function. Anyway, today I am going to discuss Schrödinger's equation. You know the Schrödinger's equation. If you know Newton's laws of motion, in the field of classical mechanics, you know this law exists. Okay, in the field of classical mechanics, and you know the use of the law, not laws, because three laws are there: first law, second law, and third law. Similarly, in case of quantum mechanics, you know that quantum mechanics is used for the particles at the smallest scales, means at the quantum level. Okay. So in that case, instead of using Newton's laws, this Schrödinger's equation, this is used. Okay, because if you apply Newton's laws of motion at the quantum level, then you will get erroneous result. Means results won't match with the experiments. So different equations are there, such as I have already mentioned Schrödinger's equation. Okay, this is a complex valued equation. Actually, it involves a variable which is known as wave function. Okay, this Schrödinger's equation, this involves a variable which is known as wave function, and wave function is a complex valued function, means a complex number iota, which is equal to root over of -1, exists in that equation. There are two forms of Schrödinger's equation. Okay, two forms are there. One is time dependent form and another one is the time independent form. First, the time dependent form of the Schrödinger's equation was derived, and using or by taking the help of Schrödinger's time dependent equation, time independent equation was derived. Okay, so purpose is what? Purpose is to know each and everything about the particles' position, momentum, energies such as potential energy, kinetic energy. So many variables are there. In case of dynamic problem, you know that. Okay, so these variables can be known by solving this Schrödinger's equation. So what is the form of the time dependent equation? The form I have already noted down here. This is the form. Okay, you can see that this is iota, then h bar is there. Okay, this is called h bar or h line also. Okay, and here partial derivative is there, del t of psi xt, and here it is h hat. Okay, then psi xt. So here psi xt, Greek letter psi is there, within bracket x comma t is there. Here h hat psi xt, this denotes the wave function, which is complex valued function. Okay, and here this h hat, this is an operator, mathematical operator known as Hamiltonian operator. And here partial derivative is there. Here in the denominator t appears small t, which denotes time. Here within bracket psi xt is there. X denotes spatial coordinate. Here I have written this equation only for one-dimensional case. Okay, you can also use two-dimensional and three-dimensional forms also. It depends upon the requirement of the problem, whether the problem is two-dimensional or three-dimensional. Okay, and here I have written for simplicity the one-dimensional form, and h line or h bar is there. This is usually called as h bar. This h bar is the reduced Planck constant. So this is what? This is time dependent form of the Schrödinger's equation. Okay, because it involves time t, and here the Hamiltonian operator, this depends upon time. This is time dependent Hamiltonian operator. Hamiltonian operator is what? It is the summation of total energy, that is kinetic energy and potential energy. It takes care of kinetic energy and potential energy terms, this Hamiltonian operator. So this was the time dependent form of the Schrödinger equation. By using the same equation for stationary problems, okay, for bound state problems, time independent form is required for the solution of problems related to quantum mechanics. And time independent form of the Schrödinger equation can be derived using the time dependent form. And the resulting equation is this: h hat psi x is equal to E psi x. Okay, here psi x is what? This is the wave function, and you can see that t is absent there, means time is absent because it is time independent. So here the wave function is a function of only the spatial coordinates. Here also I have written only for one-dimensional form. This can also be used for 2 and 3-dimensional forms, means 2 and 3-dimensional problems. Okay, and here again this h hat, this is nothing but the Hamiltonian operator, and here capital E I have written, this E, capital E denotes energy eigenvalue. I'll make separate video to discuss this energy eigenvalue. Okay. So E denotes what? Capital E, it denotes energy eigenvalue. Okay. And Hamiltonian operator, I have written this form here. Hamiltonian operator is denoted by this: minus h bar square divided by 2m. Here h bar, I have already mentioned that h bar is reduced Planck constant, and here m is the mass of the particle. Okay, and here d2 dx2 is there, x is the spatial coordinate, plus vx is there, vx denotes potential energy term. Okay, vx denotes potential energy term. So this was all about the equation. There are so many problems which can be solved using Schrödinger's equation, such as a particle in a box problem. This is a standard problem. Okay, all these things will be discussed in separate videos. Particle in a box problem is there. Then problem on hydrogen atom is there. This is standard problem. Hundreds or thousands of problems exist, but as standard problems, these are normally discussed in your textbooks. Harmonic oscillator is there. And if you talk about the field, yes, in so many fields of physics and chemistry, this Schrödinger's equation is used. Again, in case of quantum computing also, for to design the algorithms and for the understanding of quantum bits, that is qubits, the knowledge of this equation is required, means Schrödinger's equation. In case of chemistry, to understand properly chemical bonding and reactions, so knowledge of this equation is required. For again, in case of solid state physics, to understand properly the electrons, dynamics of electrons in semiconductors and superconductors, the knowledge of Schrödinger's equation is required. Okay, so many fields are there where knowledge of this is required. So these are the equation, and means this is the equation, and this equation is applicable for all the problems. So there are few steps, okay, to solve such equation. This is partial differential equation, and since this is differential equation, so it needs boundary condition to solve the given problem. So to solve the problem, first of all, you have to define the potential energy term and the kinetic energy term. First of all, you need to define those things for the given problem: potential energy term and the kinetic energy term. Okay, then you choose the appropriate boundary condition to solve the given problem. For different problems, boundary conditions are different. Okay, so next step is to choose the boundary conditions, appropriate boundary conditions. Then you solve the differential equation. So if the problem is time dependent, then you will get psi xt, means wave function. If the problem is time dependent, and if the problem is time independent, then you will get psi x, only psi x. Okay. After getting this solution, you have to check for the accuracy of the solution. Okay. And last thing is that this psi xt, this is what? This is wave function. It tells us about the variables or the parameters of the fundamental particles in a quantum system. Okay, the square of the modulus of the wave function, it tells us about the likelihood of finding the particle at a given position at a given time. Means in a particular region of space at a given time. Okay, that is what? Square of the amplitude of the wave function. That gives us the likelihood of finding the particle in a given region of space at a given time. And psi xt, that is nothing but probability amplitude of finding the particle at a given position and time. That is called wave function. And just by using this wave function, all the variables of interest can be found out. So those things will be discussed in separate videos. In only one video, that is not possible. Okay, so this was all about today's lecture. The topic was Schrödinger's equation. Okay, so this is the end of this video. Thank you for watching this video.